6.2 magnetic force on moving charge. Here is you have a charge is moving in magnetic field. The force it experiences is equal to Q, the charge. V is the velocity of that charge. B is the magnetic field present. And sine theta is the angle between the velocity, the direction of the movement, and the magnetic field. Now, what is this direction of this force? We use the right hand rule. If this is electron, you use your you use your left hand, but if this is a positive charge, you use your right hand. You put your forefinger in direction of magnetic field. Your thumb, you put in direction of the charge moving, and your direction of the palm will give you the force, the direction of the force. Here, your palm is faced up. That's why direction of the force is up. So let's just look at an example. You can try to understand. So here is the B field is downward, right? So you put your forefinger in the direction of the B, your thumb in the direction of movement. Okay, here I put my finger down in the direction of the B field, and I need to rotate my hand in a direction that the V is. Maybe I just like that. Now my palm is going into the page, right? As you see, force of electromagnet is going to be here. So the direction of the palm going to be this way. You need to try that yourself. Here is a question that's helping you. Here is the electron. The direction of the magnetic field is into the page, right? And your palm is that. But since it's an electron, you have to use your left hand. Forefinger into the direction of the magnetic field into the page. You rotate your hand, that your thumb go into the direction of the velocity. I'm talking about this one. Your palm is down, right? It means your force is down. You can try at the other point, and you see that if the electron is here, it's going toward, like through a loop, through a circular path. Okay, let's just look at this question. An electron accelerates from rest in a horizontally directed electric field through the potential difference of the 46 volts. The electron then leaves the electric field, entering the magnetic field of the 0.2 Tesla. Directing to the page. Calculate the initial speed of the electron upon entering the magnetic field. So we have a delta V, we have a B magnetic field, we have mass of the electron, we have charge. We want to find the initial speed of the electron upon entering. So knowing that work done is equal to change of kinetic energy, the work done, so potential difference is given to us, multiplied by Q, is half length between, is the gaining velocity when it's entering, right? You range for velocity. Then when it's enter, you want to find the magnetic direction of the magnetic force. You know the equation of that. You just got the velocity from previous step. Q, we know B magnetic field, we know sine theta. Theta is a direction. So look at the velocity and the magnetic field. They always perpendicular, right? It's like on the page and this is into the page. Always 90 degree. So this force will be 1.3 10 power negative 13. Sine 90 is 1. Okay, part C is that calculate the radius of the electron circular path. So since it's going through the centripetal movement. So the force is equal to centripetal force. The magnetic force, which is QVB, that force that you got there is equal to mv2r. You just rearrange it for r, and that would be the radius of this circular path is going through. So you can try question number 2, 3, and 4. So here's the charge to mass ratio. Here's a device that you are firing an electron, give it a velocity. It will go through the coil. Some of that it will pass without energy, and some of it will deflect. Okay, so it's going through the circular path. So F of m is magnetic field is EVB sine sine theta. Sine theta is always 90 in this case, so it's going to be 1. So circular path gives me mv2 divided by r, because F of centripetal is that. So E over m is VBR. V is the velocity I'm giving to the charge, and B is the magnetic field, and R is the radius. All of that we can calculate, right? And can calculate the mass to charge ratio. Instead of the velocity, I can put E divided by V. Using that, since the electric field is equal to electric force, then you just change those voltage in such a way that there is no deflection. It means the electric field and magnetic field should cancel each other, right? That's why there is no deflection. Then F of E is equal to E multiplied by electric field. You rearrange it for velocity, and you find the velocity of that, which is E over P. Then, and instead of the velocity here, we can find electric field over the magnetic field. And if you know all of that, electric field, magnetic field, and the radius, you can measure. You can find the charge to mass ratio. Here is the question: calculate the mass colorine of charge 1.6 10 power negative 19 accelerated into mass spectrometer through a potential difference of 2.5 10 power 2 volt into a uniform 1 Tesla magnetic field. The radius of the curved path is 1.35 centimeter. We want to find the mass of the colorine. So we use the same thing. QVB is mv2r. Why? Because the force need to be equal to the centripetal force. Also, the half mv2 is equal to q. So work done is equal to change in kinetic energy, right? If we isolate for V here, the V is QBR over M. Isolate for V here, then equal them to each other. Square both sides. You will get your mass. Is QB power to R power to 2 delta. That will give you the mass of the charge. So here, as you see, this magnetic field here is not uniform. That's why when the electron coming, it will go through the circular path. But as you see, the circular path will not be same radius. It's just will have this kind of shape, like a spiral electron.